She wants Derek back, so they're probably not going to go to prom together.
Yeah, they were.
Who thought?
Which one? I don't remember.
What's different about example 6 compared to where we were at yesterday? What's different about this?
There's subtraction.
There's more X's.
There's subtraction, and you have multiple terms. We have both the 2x and the 1/2 x squared. So now you're going to see what happens when we have multiple pieces. We're going from 0 to 4. We start with the same thing that we always do. Shh. What is the width of n rectangles?
4 over n.
Excellent. 4 over n. Yep, 4 over n. For what x values do we evaluate the sum?
4i over n.
4i over n.
Are we gonna have like situations where it's not 0 to?
Yep, that's the next one we do. So those are the 2 examples we do today. Today we want to see what happens when we have more than one pole or more than one term, and we also want to see what happens when you don't start at 0. So the definite integral will be the integral from where to where?
0 to 4.
Of the function, which is 2x minus 1/2 x squared dx.
I have a question.
Yep.
If I mix up and put like 4 on the bottom and 0 on top, is that wrong? Yeah.
So what's crazy about math is you can actually integrate backwards. This is called integrals, and you can integrate forwards, you can integrate backwards. And so it does change value.
But like writing it
Suppose you did it on the test?
Yeah.
Yep, I am. I'm going to hold you accountable to that. Put the lower number on the bottom, put the taller number or the bigger number on the top.
Are you being
How would you get a different answer?
It produces negative.
Well, I'm not going to, I don't
You integrate backwards, it produces a negative result.
Oh, that makes so much sense.
Wording, I think we should do some.
In mathematics, it can. In real life, we're bounded by these positive things, but in mathematics, we
But
say,
you're
why
pretty
does
negative.
I was gonna say.
Okay, Addie, when you laugh at her, it only encourages the behavior. Okay?
Keep laughing.
So if you
Hey,
could-
but you said she was funny and she'll make us laugh.
Yeah.
You quite literally put my quality as
Whoa, I didn't say funny personality. I was thinking funny looking. All right, so equals the limit as n goes to infinity
That's such a lie.
Ooh, that was a good sign.
of the sum from I equals 1 to n of, now what do we do?
Oh, that's actually pretty good. Plug 4i over n into the function.
Excellent. So 2 times 4i over n minus 1/2 times 4i over n quantity squared. And we take all of that, the entire thing, times 4 over n. Definitely got a little bit of algebra to do there, right? But let's admit, we see exactly what's going to happen now. All we have to do is do a little bit of algebra, and then we plug in a couple known sums, and then we let it go to infinity. That's the process. So from here on out. So let's knock this thing out. We'll try to be careful because likelihood of making a mistake increases here. So limit as n goes to infinity of the sum from I equals 1 to n of. Now I'm going to put a couple sets of parentheses here and a 4 over n there. All right, what do I get for my first term? 8i over n. Minus, what am I going to get there?
16i squared over 2n squared.
So can I do 8i squared over n squared? Something important I want you to notice at this time is that you have an I and an n. You have an I squared and an n squared. See how that matches in degree? After you multiply through, the n's should always be 1 degree greater than the i's. So now we're going to multiply through. I have the limit as n goes to infinity of the sum from I equals 1 to n of, what do I have now? 32i over n squared minus 32i squared over n cubed. So if you're ever making a mistake, you can look back and recognize that your I should always be 1 degree less than your n's at this stage. And finally, one last piece here before we start to look at our known sums. I'm going to factor everything out but the i's. And so I have the limit as n goes to infinity of, I'm going to factor out the 32 over n squared, 32 over n squared, times the sum from I equals 1 to n of, what's left over? What's left over here? I. And then we will minus,
Oh, you're doing minus.
and now we'll factor out 32 over n cubed.
I squared. Wait, what?
Oh, he's just doing it 12.
I split it into two parts. So notice that this just says a sum. So I have really two different sums here that I'm subtracting. So I just wrote the expression as two different sums, one limit. See if you can locate in your notes, what is it that you substitute here? See, what is it that you substitute there? Okay, take a glance at it, see if you can find what our substitution is.
N times n plus 1.
Yeah, for the first one, did you see we have n times n plus 1 divided by 2? Everybody okay finding that? If you ask why do we do that, then we go back to last year, the last 4 days of class where we did mathematical induction. That's why. Emma kind of smiled because she had fond memories of that time, right?
No memories.
Awesome. We love that she never forgets it. Steel trap, we say. Okay. And then this one is 32 over n cubed. And what's the thing that we plug in there?
N times n plus 1 times 2n plus 1.
Good. Aaron's got that. Don't have to memorize that for the test. That sits over 6, I think.
Yep.
So that's my new expression. And now it's time to find that limit. So we'll try to reduce a couple things here. We'll have the limit as n goes to infinity of, what would you like to simplify first? The 32 over 2 and one of the n's? Can we do that? So I'm left with 16 times n minus, or n plus 1 over just n. Minus, looks like one of the n's will cancel here. And what's 32 over 6 reduced to? How about we divide each one by 2 and go 16 over 3?
Yeah.
So 16 times n plus 1 times 2n plus 1 all over the 3n squared.
Crazy.
We've been pretty careful. Aiden, you were going to say?
5.3.
This part? Yeah, it will end up being 5 1/3. We'll go ahead and show the algebra anyways. We have the limit as n goes to infinity of 16n plus 16 over n. What are we going to get here?
32n squared.
32n squared. The middle is going to be 3n times 16 will be that 48n. 16 all over 3n squared. What do we factor out of that first expression? Just n. I get 16 plus 16 over n, all over n, minus n squared, 32, 48 over n, 16 over n squared, all over 3 squared. All right. Now's the fun part. We simply reduce the n's. We reduce the n squareds. 16 over n, 48 over n, 16 over n squared all go to 0. How come?
Because it's over an infinite amount.
Yeah, over a very large number, so therefore it's going to head there. So you can see that you're left with 16 there, and a 32 thirds there. Nice little common denominator of 3 would be 48 over 3 minus 32 over 3, so 16 thirds, or 5.3 repeating. Do you think we're right?
Sure.
I'm going to quick do a check here. We have 0.5x, or it's 2x, excuse me. Lily is laser focused today. 0.5x squared. She won an amazing game of Hangman.
Just because I was the one who knew things.
This is true. I'm not as good at it as you are. And I'm going to calculate the area, and I'm going to go from 0 to 4. We have 0, and we have 4. 5.3 repeat.
Wow.
Pretty cool.
When would we like use this like generally?
The applicability of this is nothing.
So why did we learn it?
You didn't let me finish.
Okay. You stop talking.
This is really, so to speak, a kind of there's two methods to calculating area. One is by using what we call this Reimann sums. So Reimann, mathematician, and kind of some of his work, you see this as the introduction to his work as you move on. It's very, very, very theoretical. But you notice that we first express this. So this is the Reimann sum. This is the integral. The integral, yes, without a doubt, gets used significantly. So just like we ended our last unit talking about optimization problems and everything of that nature, the integral has even more application, I would say, than the derivative.
Like, what job would I need to use this?
Not the job you're going for.
Well, I know. I just want to know which ones to avoid.
He's speechless.
No, I'm trying to think of an application that would work readily within everybody's minds right now. So we'll use this as a general application, okay? All right. So everybody agree that, say, the population of fish in a lake. Agree that changes over the course of a year?
Yeah.
Okay. And if you look at the population, you could represent population, say, as an area, so to speak. Okay. And the integral can help us determine that population. It can help us determine the average population. All sorts of pieces that work. So is it used? Without a doubt. Do people actually use the integral manually within their work? Folks, just about everything now is computerized. But as I talk with people who work in the industry, do I talk to people who say, yeah, you can tell who actually knows it and who doesn't? Yeah, without a doubt. Just speaking to somebody the other day, was at a wedding, great time, you were sitting around and visiting. So-and-so was talking about how they are in the field right now. They're an actuary, okay? That's what they do. Another one is working in computer science. And both of them said that some of those who entered the field a long time ago, some of the math requirements were not as high, and they find themselves having to teach some of the older people why some of these things work and how they work. So there's applicability there. So, all right. Our last example for this piece. area beneath 4, 2x minus 1/2 x squared from 2 to 5. Lily, what's different about this one?
It doesn't start at 0.
Doesn't start at 0.
It's 3 over n.
Exactly. 3 over n is our width. She ate her Wheaties today for lunch. Way to go. Or for breakfast. Who
lunch. I don't
knows?
eat-
Okay.
You ate wheat then?
Okay.
So now, because we don't start at 0, we start at 2. So if we started at 0, the x values would be 0 plus 3i over n, which was always just that 3i over n, right? But now, because we're starting at 2, we have 2 plus 3i over n. So that's the only change.
Oh my goodness.
Everybody see that it's going to be a little bit of a pain in the butt, though, when we plug that in?
Yep.
Yeah, but fortunately you're really smart and you're good at algebra and it's your favorite thing ever. So the integral is going to be from what to what? 5. Thank you. 2 on the bottom, 5 on the top. 4 plus 2x minus 1/2 x squared dx. And that is equal to the limit as n goes to infinity of the sum from I equals 1 to n of, I'm going to have something here. What do I do there?
4 plus 2 times 2.
Good, yeah, I got to plug all that in. So 2 times 2 plus 3i over n minus 1 over 2, 2 plus 3i over n quantity squared. And then we have our times 3 over n in the process. Well, that's a little bit uglier, isn't it?
Mm-hmm.
Yeah. I would say at this point, it's only normal to try to keep a certain pace. Every time I come across these problems, I take a deep breath and I try to slow my pace because the chances I make a mistake are extremely heightened. So I try not to skip steps, slow pace, take your time. Lily, you had a question or comment?
I was just saying.
The hand went in the air.
Because when you go fast, you just.
Yep. So here we go. Limit as n goes to infinity of the sum from I equals 1 to n of. I guess we'll simplify the parentheses first. I have a 4. Then what?
4.
A 4. Then?
6i.
Yep, I'm going to have a 6i over n. Remember, when you multiply by that 2, it just multiplies the numerator, not the denominator. Minus, I'm going to write the 1/2. I'm not ready to do that all in one step. So I'm going to take 2 plus 3i over n, and I'm going to square that. Yep, I get a 4. What's going to be in the middle? 12? 12i over n? And then what's going to be at the very end? 9i squared over n squared. And notice I hesitated to multiply it all through by a 1/2 because I was afraid of the mistake that would maybe be made. So I just wrote the 1/2. I'm going to take the extra time. This is pretty involved. Limit as n goes to infinity of the sum from I equals 1 to n. And I can even maybe combine a few like terms here. 4 plus 4 is 8. 6i over n minus
2.
dos, which is Spanish for 2, minus 6i over n minus 9i over n squared.
Wouldn't it be
It's
2
not
n
9.
squared?
Wait, what?
It's 9i.
Squared over.
Or 2n squared, excuse me.
You need a square.
I squared.
I squared. Yes, thank you. Yep, easy to make a mistake. And so a few people let out a gasp earlier because,
The 6i over n is canceled.
yeah, so even though our first one had 3 terms, notice that the 6i over n and the negative 6i over n do fortunately cancel. We have the limit as n goes to infinity of the sum from I equals 1 to n of 8 minus 2 is 6 minus 9i squared over 2n squared times 3 over n. Oh, we made that much smaller, didn't we? That's fortunate. So the limit as n goes to infinity of the sum from I equals 1 to n of 18 over n minus 27i squared over 2n cubed. See if you can look at your work and figure out what are the things that we substitute at this time for our sums. Take a look at your stuff. What do we substitute? There are 2 substitutions. So for the I squared, we've gotten used to that. That's n times n plus 1 times 2n plus 1 all over 6. And then this is a constant. When you factor out the n, you'll just be left with 18. And so you substitute the constant of 18 just times n. So those are your 2 substitutions. Is that clear for everybody?
Oh, never mind.
Now to be clear, you could factor out the 18 over the n and then leave the, or you could leave the 18 or factor it out. It seems that people get more confused if there's nothing left. Do you know what I mean? So if I just have a 1 there, people get confused. So I like in this situation to leave the 18. I think it makes sense for people what we do. All right, we're almost there. Limit as n goes to infinity of the sum from I equals 1 to n. Oh, I don't need that anymore, do I? Silly Mr. Gintz. Making mistakes right and left. Let's see here. We're going to have the 1 over n factored out. And what we replace is the constant, which is 18 times n. I skipped a step there. Is that okay by everybody?
Yeah, I think so.
Minus, what will be the thing sitting in front for this part?
27
Or 2n cubed, good, times that thing, n plus 1, 2n plus 1, all over 6. Isn't that nice? Limit as n goes to infinity. This one I end up with just 18. So all we have is just one expression left to work with. Notice that the n's reduce here, so we have an n squared. And the 27 over 6, Hannah, you ready to reduce that?
3.
Good, they're both divisible by 3, so we've got a 9 over 2.
Yeah.
Good. So I'll write that out. 9 times n plus 1 times 2n plus 1 all over 4n squared. I multiply through. 18 minus, what am I going to get in the top?
18n squared.
18n squared is 27n plus 9er. Divide by 4n squared. 18 minus n squared, 18 plus 27 over n, 9 over n squared, and 4n squared. I remember in a calculus class in college, we at times asked the professor, we could see right away the answer is going to be 4 or 9 over 4. So really, do we have to do the last couple steps? He said, absolutely. He said, and you should take joy in it because you can see that as n goes to infinity, that's why it goes to 0. And that's why it goes to 0. And that the n squareds cancel out. And so we get 18 minus 18 over 4, which is 9 halves. 18 is the same as 36 halves minus 9 halves, which is 27 halves, or 13.5. And that is the exact area.
Do you want our answers in fractions or decimals?
I don't care.
Okay.
You can do either or. It is important, I will say, that I can see your work, that I can follow your work every once in a while. And somebody who is not here right now might have the tendency of allowing their work to roam a little bit on their paper. There's another person in class that might allow their work to roam on their paper from time to time. And so if your work does not go, if your work sometimes goes around like this and you find different places, that's gonna be hard for me to follow, okay? And so I sometimes try, but there's a point where sometimes I give up. I kind of have that time limit as I'm looking at your problem. If a minute goes by and I'm really struggling to see your direction, then it's not good enough, and I start taking points off. So yeah, try to write it out. That's that. There you go. Nice job. You guys are now able to complete that assignment. Way to go. You took this. You want to play a quick game?
Yeah.
Okay.
I have a question first.